Hello, welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and in this video, we will learn about gradient descent in deep learning. Gradient descent is an algorithm used to train a neural network. So for training a neural network, we usually have some data, we have some features, and we have some labels. The features is the data, and the features of the data, and the labels are the answers, the actual values that we're trying to predict for that data. Labels are the answers essentially that we know ahead of time, and we want our model to be able to predict those as accurately as possible. Now, the gradient descent algorithm basically makes a prediction for those labels, for the answers, and then checks against the actual answers that it should have gotten, and then from the difference calculates some error. And then the gradient descent algorithm calculates an error function and then minimizes that error function such that the error gets smaller and smaller until it's minimum, as small as possible. And the more minimum, the smaller the error function, the more minimized it is, the greater the accuracy and the predictive power of our neural network. And it's called gradient descent because in calculus, the gradient of a function is a vector that points in the direction of greatest increase, of fastest increase of the function. So gradient descent is the opposite, is the vector pointing in the direction of fastest descent, fastest decrease in that function. So it makes sense. We want to minimize our error function to increase the accuracy. So here I already wrote the code, so we can save time. We can just go through it together. So first of all, we want to import just some basics here, matplotlib as usual, numpy, pandas, and here I created some helper functions for plotting and drawing the lines. It's not that important. You can pause the code and take a look at it here, what I did. So we basically have some student data, just two features, x1 and x2, and labels y, and the labels are 0 and 1, and this data corresponds to whether a student was admitted or not admitted into school. So here again, pause the video here if you want to take a look. Did some list comprehensions here to prepare the data, and it's just to help plot it here. So here in this next part, the data, I'm using pandas again to read this CSV file that I have in the directory, and then I'm going to plot them here using a matplotlib. So this is the data, and red corresponds, as I put here, to admitted, and blue here to rejected. So these are the two different points, and then x1 and x2 are the two features. And then there's a third dimension, so to speak, you could say, but that's just, we're characterizing it by the color here of those labels. So again, we want to find a line that best separates these points, that minimizes the error, the line that will, a boundary that will best separate these points. So as usual here in neural networks, we will initialize our weights and bias to random values. And probably the line, we're going to get a line, and it's going to be random, so it could be in any really direction, any given slope, and any y-intercept. And gradient descent will minimize the error, and then increase those weights and the bias, keep changing them until we get a line something like this, something that's cutting across the points, that's separating them the best. So we'll implement some basic functions here. So first we have the sigmoid activation function, and this is just a nonlinear function that takes in an input and squishes the output of that the values here of the input to between 0 and 1, essentially, to give us a probability from 0 to 1. That's why. So we have a linear function, some y equals mx plus b, and then we put it here into the sigmoid. We apply the sigmoid function on it, so it returns a value from 0 to 1. And then and don't worry here specifically what these formulas mean. This is just from taking derivatives. These were derived. So the prediction Again, like I said, y hat is the label that we're trying to predict. Y is the label that we have, and y hat is the label that the model is predicting. And then their difference is going to give us the error, and then we're going to minimize that error. So again, see here you have the sigmoid, and then you apply it to this linear function. As you can see, a product of the weights with the features plus the bias. And again, our error function here is a function of our label and our predicted and our prediction, and it's a function of their difference. And here we have this error function, which is in the form of logs. We have other kinds of error functions, but this is the one that we will use today. It's a pretty common one. And then this is the function, this is how we're going to update the weights and the bias. So the weights is going to be updated by adding a term here, which is, so the ith weight is going to be updated by adding alpha, which is the learn rate, the hyperparameter, we'll get to that in a moment, times the difference. So this is the error, the difference between the label, the actual value, and the value that the network predicted, times the ith feature. So that's how we update the weights, and we nudge, and the weights again corresponds to slope. So we can change the line from whatever it was, so the slope adjusts to, so it gives us the minimum error. And the bias we just updated like this, adding this, just the learn rate alpha times the error. So here we'll define these functions in code. So same thing, we just have these, but just in the equivalent of code. So we define a sigmoid function, and we define the output here, formula, the error function here, and update weights function. So it's going to return with the NumPy array version of the updated weights, and then the updated bias. So again, you can just pause the code here, take a look at what I'm doing, but it's pretty simple, pretty straightforward, just grabbing these mathematical functions here and putting them in code form in function, defining some Python functions here. So now we go to the training. So now that we have our functions, we have everything that we need to help us iterate the gradient descent algorithm through all the data for a number of epochs. So again, our hyperparameter here that we just talked about was the learn rate, and that's how big are the steps that we're going to take downhill in that error function. So we can get to the minimum value, and you can adjust this to take larger or smaller steps. And epochs is how many times do you want to run? You're going to run through all the training data, and so to get smaller and smaller and smaller error. So each epoch is going to go through all the training data and do the gradient descent. So we see we're going to do it 100 times. So I'm going to loop through the epochs. So now, and here we're just getting some random values here, some random values. So we're going to define now a train function, and it's going to take in the features, x, and then the target, which is really the labels, y, and then epochs, the hyperparameters, and learn rate are hyperparameters. And this you'll see in a moment, it's not important right now, and this last parameter here. So here we're defining some variables here. So we're going to grab the number of records and the number of features. So if we grab features.shape, so features is again our data, our features, and the rows are the number of records, the number of data points that we have, and then the features, the columns, is the number of features in each data point. In this case, 2, just x1 and x2. And that can, in this case, it can correspond to grades in an exam, or some other feature that would tell you, that would be important to deciding whether a student is admitted or not to school. So shape gives us a tuple here with rows and columns, the values, then we store them in these variables. Now, don't worry about these right now. The loss, we'll get to them in a moment. So we have the weights, and then we're initializing the weights here. We're grabbing random values from a normal probability distribution. So we're grabbing numpy.random.normal distribution, and this is just a scale factor. It's a nice scale factor for those normal values. And then for the size of this weights array, we want the size to be the size of our features, of our n features. So however many features we have is the size of our array. And this makes sense, right? Because we're going to do matrix multiplication of weights and features, as you can see here, because this is what we want. So the dimensions of the arrays have to match. And bias, we just initialize to 0. So we have our initial weights, initial bias. And again, because these are random, the line, the slope, it could be really in any direction. Well, it's going to be at 0. The y-intercept is going to cross at 0. But the slope could be anything. And again, we're going to use gradient descent to find the optimal weights and iterate that such that we get the best possible line that minimizes the error. So we're going to loop through the epochs. So that's how many times we're going to run through all the training data. And here we're defining a variable called del W, which is a small change in the weights. So for that, we're just going to initialize it to just zeros, to just the zeros here. And the weights, again, the shape has to match the weight. So we're just going to grab weights.shape here as a parameter. So this is just going to give us a NumPy array of just zeros. And then we're going to add, remember our function here, we're just going to keep adding to that. So, okay, so we have our epochs, and then we're going to, say for X and Y, which are our, so zip features and targets. Zip is a Python function that creates tuples out of the parameters, so element Y. So the first feature is going to be paired up with the first target or the first label, and so on. We have X and Y corresponding, so with the features and its corresponding label, the actual value that we're trying to predict. So very nice. So here we can just access them together. So output, error, we grab the functions that we defined here. So output formula, and as we defined it here, and we just pass the appropriate parameters. And here you can again pause the video just to see how things are passed, just to check that it matches. Just going to calculate the output here, and again, if you remember the output here is the output formula is going to be the output, what we're trying to predict, and then is our linear function, our matrix multiplication plus the bias for weight, and with the sigmoid function applied to it. So the values are squished between 0 and 1. So again, so error, so we get our error, our logarithm, and our log form of error. And then here we have our weights and bias. And again, we call our update weights function that we defined here, and pass those in, and it's going to give us the updated weights and biases. The updated weights and bias, and we store them here in this variable. And this is for each one of the features and the label in this in here. So once we loop through all of the data, and again, this is still for the same epoch, now we're going to define so the output here formula. And this is for printing out the log loss error on the training set. And you'll see in a moment just why I'm doing this. And here, so every 10 epochs, we're going to print some information just to show you the progress of the network. And here you can pause the video, look at the code, what's going on. But essentially, if the loss we want the loss to be decreasing, and we're going to show you the accuracy at the each multiple of 10 of the epoch, each multiple of 10, so you see how the accuracy is increasing, or in worst case, the accuracy is decreasing, so the loss is increasing. And I put in a warning here, a case where the loss is increasing, just in case the algorithm there was an error, so you can see. But a lot of this is not really important. It's just for really visualization purposes, for you graphing some lines, plotting the solution boundary, plotting the data, and so yeah, so this is our train function, and we're going to do this for this code right here. We're going to run it for all of our 100 epochs. And again, you can adjust the hyperparameters here. You can tune your hyperparameters. And so now we're going to go ahead and train the algorithm. So let's run this part. So okay, so we have that. And now we're going to train. So here, now we're going to call the train function. That's it. So all we did here was define the train function to train our neural network, pass the features, the labels, and our hyperparameters. And now let's go ahead and see. Oh, actually, yeah. Let me actually go ahead and just run everything from the beginning. So we do restart, clear output. Now run all of the cells. And here's, you can see we're printing out some every epoch, every 10 epochs. So 0th epoch, so the accuracy, as you can see, is 40% initially, not that good, pretty high loss. And then on epoch 10, better accuracy. Now we're around 59%, and the loss is decreasing. So that's good. So we're minimizing the loss. Gradient descent is minimizing this loss. It's updating the weights and the bias and updating our function, our function here, parameters, such that we get smaller and smaller loss and higher accuracy. So as you see, there's an inverse correlation. The loss is decreasing and the accuracy is increasing. So as you can see here, it starts, the gradient descent steps as they get smaller and smaller once you approach the minimum of the error function. And here it converges at about 94% accuracy. And here you can see these beautiful plots here. So this was the random values that we started. So the random weights, values here, the slope here, and then with each gradient descent step, the weights, so the slope was updated, and then updated again, and then updated again. So and the bias as well, the y-intercept was also, you see, it's also changing. So this line was the first one, and then it gets better and better and better and better and better. And you see it makes this beautiful kind of fan pattern where it converges on this last line with 94% accuracy. And that's exactly what we would expect, the line that splits our data points the best. And this would be a logistic regression problem for classification, because the error is a log function here. And as you can see, the error starts pretty high here in this logarithmic plot, and the error, as gradient descent, as the number of epochs increases, gradient descent algorithm is running, the error is decreasing as a function of the number of epochs. And once we reach the 100th epoch, we are at the minimum value for the error, which corresponds to 94% accuracy. So I just think this is absolutely beautiful. And so, yeah, so that's how you do simple gradient descent in deep learning for neural networks. And again, this is just so you see how it works. But normally using TensorFlow or PyTorch, this would be done for you. Those modules, you can import functions that can do this for you. But it's good to know how things are working behind the scenes. So thank you for watching. If you have any questions, thoughts, comment below, and I will see you next time.